Hi, everybody. It's nice to be here again. To see these meetings is still going. I actually gave a talk on the second research seminar TT Lab ever had when it was back when it was weekly meetings. And then a year after that, I gave one. And now I'm here a few months later to give another one. So it's good to see everybody again. So title of my most recent publication with Prof. Patrick Hussein is Instant Message Summarization with Emoji Unicode Characterset Support. I will go into this a bit more, but first I just want to cover some prereq knowledge. So it's just some information on how you would represent words in a computational sense. So to apply computational methods to words, we need to represent them in an appropriate manner, of course. So consider these two sentences here. I love guitars and keyboards, and music and concerts are amazing. So the first way we could go about this is using something called one-hot encoding. And this was the preferred choice of word representation in earlier models. In this case, we treat each word as a discrete symbol, which has no direct comparison to any other symbol. So again, these two sentences. And from these two sentences, we can form a dictionary. A dictionary is just a set of all the words used in our corpus. So we just take each word and extract it and to form a dictionary, a complete collection of the words used. Again, sentences. We have a dictionary here. So a one-hot representation of sentence one would look something like this to the top right here. So sentence one, so I love guitars and keyboards. Each element of this list is a dictionary where a one value symbols that word is present at that location. So for example, you'd have a one here, then zeros everywhere else. Love, ones, and so on and so forth. And similarly for sentence two, the same thing happens. So you can see that the word and is the only word that repeats. And so that from the dictionary, that's an index 3. So when index 3 is 1 and everywhere else is 0, that's the representation for and. So there's some drawbacks to this method. The main one being words are seen as independent or orthogonal to each other. So we know that there are words with similar meaning, for example, man and male, and that isn't conveyed using this representation. So that led to the creation of dense embedding representations. And this is a method of representing a given word in an n-dimensional continuous dense vector. Each dimension of the vector contains the context of an underlying attribute of that word. And these word embeddings convey much more information when compared to one-hot encoding. So let's look at how we would represent these two sentences using a dense representation. So each word in the dictionary is now represented, in this case, by 3 numbers. So just looking at the dictionary, right, this embedding vector lookup table here, we could see that if we look at the word guitars, we could see that in dimension 1, you have a low value. Dimension 2, you have something around 0.2, and dimension 3, you have a high value. If you look at keyboards, you have a low value dimension 1, something similar to guitars in dimension 2, and dimension 3 is something similar to guitars. So the main idea using this representation is that there are some words that are closely related to each other, and they have similar embedding vectors. They won't be far from each other in the vector space of the embedding vectors. So something else, music and concerts. So you can see that dimension 3 in music and concerts are very closely related, while the others aren't. So there's probably some interaction happening between those two words. Okay, so using this representation, this embedding vector table, we could create representations for the sentences. So we just replace each word with their equivalent embedding vector. So, and this last thing underneath here is just something very cool that you could do with these embedding vectors. So for example, if you take the embedding vector for king and you minus it from man and you add woman, you get something close to but not equivalent to queen. So you could do fun arithmetic here and to see what results you get. Okay, so now to the actual presentation. So we know that there's an escalating use of textual information. So, and as of 2013, a long while ago, there was 500 million tweets created per day. So I can just imagine this number has skyrocketed recently. Average instant messaging messages sent is around 72 messages every day. And there's been ongoing research to show that emojis are found to convey deeper meaning into conversations, and their meaning can change due to the context of the surrounding text. So the problem definition. So I'm going to recap the problem definition. And the best way to do that is to give an example that was given to me a while back. So imagine you're in a high focus scenario, such as driving a car, or you're in a lecture, a university lecture, and you get a text on your phone, right? And you have a smartwatch on. So you get a text message, you get a notification on your watch showing the message. The message is too long to be shown on screen, right? But say if, for example, it's a message from your mom, and your mom is saying, I know you're in class, but can you buy eggs on the way home? So a message like that, you wouldn't want to interrupt your high focus of your university lecture or driving a car to open that message to see what the remainder of the messages or what that message says. What you'd ideally like to have is a shortened version on your watch. For example, probably the emoji of eggs and the word buy from your mom. So you know that your mom is saying buy eggs. So to represent that more mathematically, we could do something like this. So we could let a message be denoted by X bar. And this message is of size length n, where n is the number of words in that message. And each incrementation of the numbers represents a different word. So what we want to do is we want to take this X bar and we want to create a summarized representation Y bar of length m such that m is less than n, and that some similarity score between X bar and Y bar is maximized. So basically we want to get a short version of X bar, and we want to ensure that the similarity between those two messages, the summarized representation and X bar, the original message, is sufficient. So a proposed method takes the input sentence, tokenizes the sentences, extract important tokens. We then create an n-gram representation of important tokens, and then we select optimum emojis. So I'm going to go through each of these steps in more detail. But something to note is that at this step here, all steps up until this step could be seen as feature extraction. So we take a sentence and we extract the best features that we can from that sentence. Then we use those features to assign emojis to different parts of the sentence. So I'll go through that now. And the best way to actually go through that is I chose to kind of strip back the mathematics and go with an example so you could actually see what's happening. So The first section is the Tokenizing Sentence. So we take, for example, the message, can we go to the beach, take my car? We take this sentence, we look at the white space character, and we create tokens, which are basically the words. Each word is a token, and we represent that in a list called X bar token. So it's the same original sentence, but we extract the words which are delimited by the white space character. Second step is that we're extracting important tokens. So we know that not every word is important to the context of the sentence. There are some words that you can do without. To do this, we use a pre-trained average perception part of speech tagger from the NLTK package, and we use this to assign part of speech tags. We assume that all forms of nouns, verbs, adjectives, and adverbs were important to the context of the original sentence. So if we take this part of speech tag and we tag the original sentence, you get something that looks like this X bar POS. And it's a result where each word is assigned a part of speech. So there are tons of different kinds of parts of speech, more than I could even recognize. So I had to reference a lot to this NLTK package and what each of these things means. So from this tagging operation, we then extract all nouns, verbs, adjectives, and adverbs. So from this original sentence, can we go to the beach, take my car? We now have go beach, take car as the important words from the sentence. Next up, the next step is to create n-gram representations of tokens. So what is n-gram? N-gram is just a way of saying the number of elements considered at one time. So for example, you could have unigram, bigram, trigram, quadgram, so on and so forth. In this case, we went up to trigram, and this is done so that words with similar meanings that are next to each other will have a chance of being represented together. So from our last step, we had go beach, take car. So the unigram representation is that each word would be considered individually. The bigram representation is taking two words at a time and sliding by one over the tokens. And similarly for trigram representation, the window size would now be 3. So after that, so up until here, we have text-based words. Now we want to create a numerical representation of these tokens. We use the word-to-vec model to create dense representations of each token. So similarly to the second slide I gave about the prereq knowledge, we created dense representations for each gram or each token in this list here, a numerical representation over, I believe, word-to-vec is 300 dimensions. So the example that I gave was 3. In reality, 3 is not enough. So word-to-vec uses 300 dimensions. So we create a numerical representation for each token, each n-gram representation. So given that we have numerical representations for our tokens, now we want to match those tokens to something to do with emojis. So EmojiNet is a data set that consists of keywords and labels for each emoji. The Unicode website also has keywords assigned for each emoji. So we combine the keywords from EmojiNet and the descriptions from the Unicode website to create a definite set of words for each emoji. And then those words were then evaluated to give dense representations of each keywords. Dense representations of each of these keywords were generated using the word-to-vec model. So similar to generating dense representations for each of these tokens, the unigram, bigram, and trigram, we did the same for the keywords of the emoji dataset. The keywords for each emoji. So now we have numerical representations of the tokens of the sentences and also the description of all the emojis. So it gets a little easier now. Now we just have to find a way to choose what emojis, given some loss score, to assign to different tokens. So to generate prospective emoji characters, we now have a collection of dense n-gram representations and dense emoji representations. So for each vectorized token in the n-gram representation, we use the mean squared error between that token and each keyword for the emojis. And then the emoji with the minimum error for that keyword is chosen as a replacement. So it's probably a mouthful there, so I'll go through a small example again. So again, we have go beach, take car, go beach, considered together, beach take, and take car considered together, and then a collection of 3 words considered together. So if we look at the dense the words that coincide with the emojis, so the descriptions of the emojis, and we look at their dense representations and compare them to our dense representations of these tokens and assign the emoji score that has the least mean squared error, these are the emojis that are generated. So you could see that go has an arrow, beach has a speech, take, oops, has a bathtub, I don't know why, car has this car. So go beach, beach, beach take car has a car, and so on, so forth. So what we want to do now is looking at the errors. We're gonna choose the token that has the least mean square error and assign that token an emoji. So E hat is a list of all the errors. We're gonna, in this case, this token has the least error, which is 0.0, which means that the word car is also a representation. It also exists in either the Unicode or the emoji dataset to describe this emoji. So we replace this emoji, well, this word or this token with the emoji of car. And then we remove all instances of the tokens that contains the word car. So then after we do that, the word car is no longer considered. So the new gram representation is go beach take, go beach, beach take, and then go beach take. So we repeat this process again. We look at where the minimum mean squared error is occurring, and that seems to be at the go beach instance here. So we're going to replace this with the emoji for the beach, which would be here. So this process is repeated until a set proportion of emojis and words is met. In this example, I set the proportion to 0.5. And so can we go to the beach, take my car? It results in this nice emoji of the beach, take car. And we have a nice little table of some other examples here. On the left side, we have the results from this method that was described. So can we go to the beach, take my car? We have beach, take car, buy some eggs on the way home, buy eggs, home. Feed me some chocolate cake, feed chocolate and what looks like a cake. I think that's a cake. Help me, I'm lost in the city, SOS, I'm lost, emoji of the city. And on the right side here, just something fun that I was doing. I was actually trying to create my own data set of labeled and unlabeled pairs so I could use a neural network to train it. I got only up to 500 or 600 messages. Data labeling is tedious and tiring, but this was the results from training a neural network to do the same task that I did numerically. So can we go to the beach, take my car, beach, buy some eggs, buy eggs, feed me some chocolate cake, turns into cake with an egg with an exclamation mark. And yeah, so this was just done just to see the performance and just to see what would happen. And it's something nice to look at, something hard to generate, for data to be generated for. And in closing, I know I skipped a lot over the mathematical equations for the error calculations and updating the n-gram representations. And that could be, if you really want to see those equations, you could have a look at the paper. You could message me afterwards. I don't mind talking about it to you. And that's the end of my presentation. So let me stop sharing.
Yeah, thanks, Darren. So those of you interested in the paper itself, it was just published this in January in Multimedia Tools and Applications.
Yes.
Yeah.
Yeah.
And I think it was available for a short period online, but we have copies if anybody wants a copy. Yeah, the publisher allowed certain copies to be certain number of copies to be downloaded, and we exhausted that very quickly, and Darren found out that it wasn't working anymore. So yeah, if you want a copy, just let us know. But what I wanna, and thanks, Darren. You did a great job. But what I also like to talk about in these sessions is how we came up with the problem, because that is one of the major issues, when you're doing research, how you come up with a problem to solve, something that is worthwhile solving, and something that is, significantly difficult to be published. In this particular case, this actually came up even before Darren joined us. So Darren probably doesn't even know the history of all this. But at the time, this was like 4 years ago, Nicholas was working on a smart bracelet that would capture, body information, as well as be connected by Bluetooth to the phone, and you would be able to read text messages on the bracelet. The bracelet was supposed to be powered, solar powered, right? So it had a small strip for solar power, and what it also meant is that the real estate for displaying a message was very limited, and so even text messages was an issue. So he asked us to come up with ways to condense the information, and so then I had suggested to him, well, how about going all the way down to emojis, and and we were even trying to come up with a metric to measure the success, in terms of a number of pixels you use, etc. So that's how this all started, condensing the information for a wearable device, and I forget who started working on it, but I think 1 or 2 people started working on it, but they didn't complete because they had to move on to other things. And then Darren took up the challenge and did a great job in completing it. So yeah, so again, it turned out to be an interesting problem to solve. It is valuable for other purposes. Maybe others might be able to use it for something else. In terms of extending the work, we could potentially extend it as well, but as you know, people do research based on their interests. So if anybody's interested in extending this work, please let us know. And that's about it. So any questions for Darren on the specifics of the solution? Again, the problem formulation is always the difficult part. The solution is also difficult in this case, but formulating the problem is one of the main things I like to focus on as well. So any questions for Darren? Okay, Darren. Well,
Oh, hey,
yeah, go ahead.
Darren. Hi, sorry, I came in a bit late, so I didn't get all of the presentation, but great job, well done. Extremely fascinated by this. I know Prof just said that you all could like distribute a copy of the paper. So I don't have any technical questions for you at the moment, but I would really like to know if I could get a copy of this paper. Sounds very interesting.
Yeah. You'll get a copy for sure. I believe the paper is a condensed version. So I actually did this solution for my thesis, my master's thesis. So I believe that should be published in UWI's library. If not, I could send you that as well.
Okay.
So
yeah,
that's no problem.
Yeah, I'll send my email in the chat, I guess. And
Well, okay, we'll also put it on the lab.tt website.
Oh, it's on our site?
I think it's I'm not sure, Shiva, if we actually link the actual paper. But if not, I'll send it on to Shiva to put on the website so you can get it there.
I think once it's available, we push up the paper with the post. So yeah.
Right. The only thing is the link we had initially wouldn't work anymore, but I have a copy, but I'll discuss that with you about that.
Okay, no, I got it from the site.
Oh, the site has it. All right.
Yeah. Okay, great. So thanks a lot. Again, great presentation, Darren.
Thanks so much.
Yeah.